For instance, here's a demonstration of how short a time interval is easily measurable today. We'll send electrical pulses through about 4 feet of wire and see if our computing counter can measure how long it takes the electricity to travel from one end of the wire to the other. Yes, you see, the measurement of the interval is almost instantaneous. It takes the pulse of electricity, let's see, that's about 6,300 millionths of a second to go through the wire. People ask us why we would ever need to measure times this short. But actually, in atomic physics, 100 millionth of a second is such a long period of time that we would hardly ever talk about it. We're more concerned with times in the neighborhood of a billionth of a second or shorter.
A billionth of a second is called a nanosecond. In the time it takes a firecracker to explode, 1,000,000 nanoseconds go by. In a billionth of a second, a jet plane will travel about 100,000ths of an inch, which is far enough for it to plow through several air molecules. Inside of those air molecules, a great deal is happening in a billionth of a second. An air molecule will find time to spin hundreds of times. Some subatomic particles will live out their entire history. Protons in the atom's nucleus will revolve thousands of billions of times in a billionth of a second.
For a long time, men considered atoms to be the smallest parts of nature. Recently, even smaller constituents of matter have been discovered, the so-called elementary particles. Over 100 of them have been classified thus far, with names such as electrons, neutrons, K-mesons, neutrinos, and antineutrinos. The lifetime, or the decay process of these particles, is extremely short. It's only to the order of 10 to the minus 24 seconds, which is 1/1,000,000th of a trillionth of a second.
In machines like this cyclotron at the University of California, atomic particles are accelerated to high velocities and studied. Physicists have seen and recorded events taking place in quadrillionths of seconds and shorter. Some such events are seen to occur in reverse time.
Of course, when we talk about backwards time, we're usually speaking of a rather specialized interaction among electrons, positrons, and gamma rays. The actual backwards direction of time only takes place for tiny fractions of seconds in localized points in space. It's not at all like the dramatic reversals of time found in science fiction.
Here we see a typical photograph in elementary particle experiments. The white lines that you see here are tracks left by the particles entering a bubble chamber.
The time intervals of particle physics are so brief they can only be measured indirectly by such methods as measuring the tracks particles leave in liquid hydrogen. It takes light a trillionth of a second to cross the nucleus of a hydrogen atom. That is also the shortest decay time of any atomic particles. Some theoretical physicists have suggested that time passes in discrete units, and that each unit is about a trillionth of a second. If we start with this as a unit of time and lay out 1,000 trillion of them end to end, we still have only a billionth of a second. Extremely brief events are as inconceivable to us as the eons that pass on stars and planets. The lifetime of a man falls about midway between the lifetimes of atomic particles and the lifetimes of stars. And our view of the universe is peculiarly fashioned by our place in time. For a man whose life is less than a century, 1 billion years is a very long time. and a billionth of a second is inconceivably brief. But if our lives were as short as the lifetime of the particle called K Meson, a second would be like the age of the universe is to us now.
We have talked about very long periods of time, and we've talked about very short periods of time. But now we aren't talking about anything. Or rather, what we're talking about now is now. How long is now? A billionth of a second? A trillionth of a second? When it's now on Earth, is it now throughout Andromeda Galaxy? Have you ever left now? Would it surprise you to learn that there are lots of places where now happens at a different time? For us, there is a continually moving point in time which we call now. This now separates the past from the future. It is always now. Time is a long string of nows which stops abruptly at the present.
Looking back on them, we see these nows as instants in time and as points in our movement through space. It has long been believed that there is a connection between motion and change and the passage of time. We sense the passage of time by noting motion and change. Indeed, that is our perception of objective time. But in order to understand the subtle meaning physicists give to time, we have to understand a more abstract concept, the notion of periodicity, of a universe of cycles. As the Earth revolves around the sun, we make a sort of clock out of it. The sun is the center, the Earth is the clock hand, and the 12 hours are January, February, March, April. But as the Earth revolves around the sun, it also rotates on its axis, and so we have days and nights. Unhappily, the rotation on its axis and the revolving around the sun are unrelated. Each time the Earth revolves around the sun, it rotates 365 times, plus a very awkward fraction. For aesthetic reasons, men have tried to work out a calendar which easily fits days into years. But the great periodic cycles are more complex than that. Today we have a complicated system of leap years and oddly divided months. The system is only now beginning to do justice to the beautifully symmetrical motion of planets and suns. Just as we divide the year into months, we divide the day into hours. One of the first mechanical devices for telling hours was the water clock, or clepsydra. It simply measured dripping water, and so worked on cloudy days and at night. About 3,000 years after the first clepsydra, Galileo discovered the principle of the pendulum. Any mechanism which is supposed to tell time must be based on some periodic motion, something that repeats itself over and over again. something that repeats itself over and over again. It might be the daily sweeping of the sun across the sky, or dripping water, or a pendulum swing, or unwinding spring. Today, most clocks mark off alternating current. 60 times a second, electricity in America goes one direction, then the other. And faithfully, millions of clocks inch forward together.
If we make a clock tick off 86,400 units every 24 hours, we should have a dependable regular second. But the Earth is turning irregularly on its axis. Gradually, as the years pass, it is slowing down.
Ultimately, the friction of the wind and tides may slow its rotation until it always keeps the same face toward the sun, just as the moon now rotates so as to keep the same face toward the Earth.
If we defined a second by the rotation of the Earth, seconds would grow imperceptibly longer with every passing day. So scientists computed exactly how long an average second had been in 1900, and that precise length of time became the definition of a second. So a certain fraction of the year 1900 is the definition of a second. In order to build a clock that was accurate enough to tick off the exact second, scientists went to atoms of a rare metal called cesium.
The principle of our cesium atomic clock is really quite simple. When cesium metal is heated, the individual atoms begin vibrating about 9 billion times a second. And those atoms are vibrating very accurately, more accurately than almost anything else in the universe. We send a stream of vibrating atoms into a little chamber that's resonating at the same frequency, about 9 billion times a second. The resonating chamber interacts with the atoms inside it. It keeps the atoms vibrating, the atoms keep the chamber resonating, and the chamber controls a crystal of quartz rock, which is sending out a radio signal. In other words, the atoms control a radio signal, and the signal controls a clock.
We have an unexpected clue as to the workings of time on the very long scale. It is the principle of entropy. The principle says that the natural state of things is diffuse, chaotic, disordered. And with every passing moment, the universe as a whole is becoming more disordered. Entropy means that an orderly little drop of ink will diffuse into 1 billion parts at the first opportunity. Entropy means that the air in your room will remain in the most disordered state possible. It will never gather together under your bed and leave you to suffocate. It means that every rock and every planet is slowly disintegrating. Everything in the universe is gradually slowing down.
As time marches on, entropy marches on. Indeed, they may be more related than we imagine. Notice what happens when we make our movie violate the principle of entropy. When the cards go to a more ordered rather than a more disordered state, it looks like we've reversed time. We can always tell when a movie is going backwards by the violation of entropy. What we conceive of as time may be simply the relentless process of entropy, of decay, of increasing randomness.
So far, we have considered time moving forward uniformly, unchanging throughout the universe. But is it possible that there are worlds in which an event taking place in 1 second on Earth might stretch out to eternities? Presumably to an insect whose life is brief and whose movements rapid, our activities are slow and lumbering. Relative size may affect our perception of time. But are there conditions under which the flow of time itself varies?
In this film, we have suggested that time is related to motion. Physicists now believe that the actual rate of the flow of time is related to the velocity that an object, or a space capsule, or a planet is moving through space. Since things move through space at vastly different velocities, this would suggest that time itself flows at different rates.
Indeed, this touches upon the great insight of Albert Einstein, who radically reformed our ideas of the nature of time. He showed that time is a personal perception, rather than a universal experience shared by all. That no one man's time is better than another's. We all perceive time at different rates.
Degrees outside, and this is WWN TV News. The big story this morning is the blast-off of the Diogenes 3 space capsule. The controversial flight leaves from Edwards Space Station at noon today, despite numerous last-minute attempts to ground the experiment. Earlier this morning, we spoke with Dr. Milan Herzog, Director of Operations for the Diogenes program.
How's it going, Dr. Herzog?
We don't expect any problems this time. No, we don't.
What about the first two voyages?
Well, I'm sorry. I'm too busy right now to answer this question.
Diogenes 3 is about ready to undock and blast off from Edwards Space Station. We are supposed to have a direct line. Yes. Yes, there you see astronauts Chris Johnson and Lin Wu. Our transmission is very bad. I believe that was the blast-off. This would be mission control in Edwards Space Station. The station itself is in a permanent orbit some 200 miles above the Earth, with some 50 scientists and engineers in residence. And of course, this is where Diogenes left from just moments ago.
As the world
If the mission goes as expected, in about 18 hours, the spacecraft will be going 150,000 kilometers per second. Of course, most interest in the project revolves around the so-called time warp experiments, or what scientists prefer to call time dilation effects. Behind me, you see one of the 3 cesium atomic clocks which will be used to measure the amount that time slows down on the spacecraft. It may sound like science fiction, but scientists say that across the face of the universe, time goes at millions of different rates as compared with time on Earth.
There are many problems in attaining velocities near the speed of light. For one thing, it takes enormous amounts of energy over long periods of time. To achieve just half the speed of light in 30 days traveling time, there would be a continual pressure of 1,000 pounds on each astronaut. And as for accelerating to, say, within 100 miles per hour of the speed of light, our astronauts would not only be old men when the speed was finally achieved, but the amount of energy consumed would be more than what is contained in our entire galaxy. So the director of the Diogenes 3 mission has conveniently invented an anti-gravity device and a superpower source, thus making it possible for the spacecraft to accelerate quickly to nearly the speed of light without pulverizing the astronauts to a fine atomic dust.
Diogenes 3 has been accelerating for 18 hours now and is doing 145,000 kilometers per second. This is Dr. Milan Herzog, Director of Operations. Dr. Herzog, what has happened on the flight so far?
Well, of course, we're delighted that the mission is going so well. At the moment, the spatial and time distortions are very obvious.
Just what does that mean?
Yes, you will notice that...
What appears to be slow motion on a television screen is actually representing one of the phenomena predicted by Albert Einstein's relativity theory. He showed that when one system was going at an enormously high velocity relative to another, time on that system would be slower than time on the reference or stationary system. We are seeing a time dilation as it would appear on a spacecraft going about 99.9% of the speed of light.
Not at all. As far as they are concerned, everything is normal on the spacecraft. But when they hear us on their radio, our voices are speeded up, like a tape going too fast.
"20 minutes ago, we began this film by suggesting that time was somehow related to movement. That's how we perceive time, through motion and change. Subsequently, we talked about clocks, and we talked about calendars. We defined a second, which is the basic unit of time in science. We talked about nanoseconds, and we talked about entropy. So, here we sit, 20 minutes later, trying to understand why the astronaut is moving so slowly. We know he is traveling very fast, at nearly the speed of light. And we know that when a body moves past us, time for it is slower than time is for us. So the astronaut crawls through his chores, his every moment stretched out. We cannot ask what he is doing now, because his now is not our now. While he is moving, he exists in a different time scheme than we do. In much the same way, every star in the sky is in a different time scheme. In physics, time means the reading of the master clock. Beyond this, we don't know what time is, but we know a few things about it, not the least of which is that we are caught irrevocably in its forward motion.
There's no use trying, Alice said. One can't believe impossible things. I dare say you haven't had much practice, said the Queen. When I was your age, I always did it for half an hour a day. Why, sometimes I believed as many as 6 impossible things before breakfast.